All right, so we have all this data. How do we actually build a model to help represent the data? Or if we have a scatter plot, what can we do with the data so that maybe we can understand it a little bit better? Or what do we need to know? First, we need to talk about a linear relationship. Think of the word linear and what it means. A linear relationship is graphically described as I'm gonna put a blank. What is it usually? If you look at a linear graph, what is it? Usually a straight what? Line. So graphically, a linear relationship is a line. Mathematically, a line is an infinite set of points that satisfy the functional relationship y equals mx plus b. So that is usually around the 7th or 8th grade, and maybe even earlier now. Your math teacher starts beating that into your head. Y equals mx plus b. Y equals mx plus b. And so, even calculators are set up y equals. A lot that if you've used TI calculators to graph, they'll say y equals. All right, and so if we have just one y equals mx plus b, then of course we know that m is the slope of the line and b is the y-intercept. Alright, so pretty straightforward. It's covered in anywhere from junior high math all the way through high school math, through college algebra. You've seen that term, hopefully. So here is an example of a graph that has a linear relationship. Hours studied and test scores. It shows how many hours that the students studied. It shows the test scores here. And I'm sure that it wouldn't be a perfectly straight line, but there could be a line drawn through the central through all of the points uniformly so that you'd have this linear relationship. Alright. And of course it would vary from person to person, I'm sure. Alright, so again, y equals mx plus b the number in front of the x, that's your slope. The number that you add or subtract to your x, that's your y-intercept. Okay. Together, the slope and the y-intercept are called the parameters. Now, while we don't have straight lines in these scatter plots, we can see that in this scatter plot, as x increases, y tends to increase. In this scatter plot, you can see as x increases, y tends to decrease. So maybe this would be education and crime rate. I'd rather it be this graph than this graph. We want those smart criminals, right? And then as x and y does not change in a predictable way, as this scatter plot. They're just everywhere. Can't really say it's going, it's increasing. Can't really say it's decreasing. They're just everywhere. That will probably be like the teacher salary and the student completion rates, so there doesn't have to be a relationship there. All right. 5.4 is on measuring the degree of a linear relationship. Now, don't get discouraged when you see this formula, because it looks very complex. Okay? This is a formula for the correlation coefficient. Alright, and the correlation coefficient is an index number used to summarize the strength of a linear relationship. Okay, and it is, the variable we use is R for our correlation coefficient. R equals 1 over n minus 1 and then we have the sum I equals 1 to n. All this means, this is summation notation. I equals 1 to n is just going to tell us we're going to have to do this for each term. Where does the I come into play? Well, it's the summation of x sub I minus x bar. So x sub I, that's a data item, minus x bar, that's the sample mean, over s sub x. This is a lowercase s, so that stands for sample standard deviation, and it's the sample standard deviation of the x. Alright? And then we have y sub I minus y bar over s sub y. R will always be between or including -1 and 1. Without having to calculate this value, sometimes this value, of course, will be generated by some type of statistical software, especially if there's a lot of data items, because imagine finding that sample standard deviation for each variable and all of that. Without having to do all of that, there are some important characteristics that you need to understand about the correlation coefficient. Then I'll show you a few example scatter plots and show you what their coefficient or their correlation coefficient is equal to. But some of the important properties of the coefficient, the correlation coefficient, is that the correlation coefficient R measures the degree of linear relationship. That is, how well the data cluster around a line. Alright, so I told you that R will always be between -1 and +1. Okay, if it's a value, near -1 or +1, means the data are tightly bundled around a line. Okay, so if you get like 0.99 or -0.97, numbers really close to -1 or 1, that means that the data are going to be tightly bundled around a line. And so if the value is near -1 or 1, then it would be very easy to predict one of the variables using the other. So if the value is close to -1 or 1. It would be very easy to predict one of the variables by using the other. Alright, just like you would probably come to the conclusion of, if you're thinking about a positive relationship, that positive association is indicated by a plus sign, and it indicates an upward slope relationship. So if you have a positive association, which is represented by a plus sign, then that's going to be associated with an upward sloping relationship. A negative association, indicated by a minus sign, is going to be associated with a negatively sloping relationship. So plus up from left to right, minus down from left to right. A value near 0 means there is no linear relationship. Between x and y, whatever two variables you have. It does not matter whether you correlate y with x or x with y, you will still get the same value for r. Does not matter if you correlate y with x or x with y, you still get the same value for r. Alright, so let's look at a scatter plot with a coefficient or a correlation coefficient here. You can see here on the right side of the screen, you can see R equals 0.95. You know, I'm going to copy this graph really quick so I can write on it. I'll copy both of those. So I could have a straight line through that set of data in the scatter plot, and all the data be very close to the straight line. Right? It's kind of bunched up around the straight line. Alright, this positive value means that we have a positive relationship. Okay, so it goes up from left to right. Now this R, it's a little bit, it's not as close to -1 as 0.95 was to 1, but still And maybe I kind of cheated at the end of my line there. But this data is still kind of grouped up around some linear line. Okay. Now what about an R that is not close to 1 or -1? See, the data is just scattered all about. Okay. So a positive coefficient correlation, you can draw a straight line that would make all of the data bunch around the straight line. A negative correlation, if it's close to -1, the same thing. If it's close to 0, then you're just going to have data items everywhere. Okay? And that finishes 5.4.